All right, so looking at 322, we have Cramer's rule. It's a modern method of solving a system of linear equations. Definition of modern is subjective, I guess. Cramer's rule, named after its inventor Gabriel Cramer, who was a Swiss mathematician back in 1704 to 1752. All right, so it's a method of determinants. I'll get to that in a minute, but what I wanted to do real quick, it's not really indicated here, but it is part of the curriculum. The addition slash elimination method for solving equations, systems of equations, I should say. So let me show you how you would apply that here. So I'm going to say, I'll call it what it is, addition, elimination method. And I'll rewrite the problem. The whole idea is to eliminate a variable through addition of equations. And there is a whole sector of linear algebra that covers this kind of thing, but this is also something that you would tackle in an early algebra class, so like Algebra 1. Right? So the idea is that you can multiply one or both equations by a number that would allow us to cancel out a variable. All right, so what I'm going to do here is I'm going to multiply my second equation by a 3. And there is kind of like an acquired taste aspect to this, where you might look at this and say, well, why'd you multiply by 3? And my answer is, I'll show you. So that's why I multiplied by 3. If it's not obvious, it's because this now allows for an elimination of a variable if I were to add the two equations together. But how did you know 3 specifically? Well, I looked at my coefficients and I said, you know what? I'd really like them to be opposites of one another. So up here, I have a -3. So I would say, well, what would I have to multiply this by? Remember, there's an assumed 1 here. What would I have to multiply that assumed 1 by to give the opposite of -3, meaning I want it to become a +3? The answer is 3. If I multiply that number 1 by a 3, it would allow cancellation. But I can't just multiply one term of an equation. It creates an imbalance. So I multiply every term of the equation, so it becomes a new equation equivalent to the first one, but having the desired coefficients. So now when I add my coefficients, all of them together, so you see how it's stacked, where the x terms are over one another, the y terms are over one another, and the constant terms are over one another. I can now add down the line here. 4 plus 6 is 10, 10x. -3 plus 3 is 0, so 0y, which is going to wipe away in a second anyway. And then 28 plus 33, so 61, I think. All right, so I can write this now as 10x equals 61, then divide out the 10, and that will give me x equal to 6.1. All right, so that's the value of my x variable. Now I need to find the corresponding value of y. So I'll take my original, one of the two original equations. It does not matter which one you take. Just try to take one that was not altered. So I wouldn't take this, but it really doesn't matter. So I'm going to replace my x. I'm going to substitute in that 6.1. All right. I'm going to substitute that in, and that's going to give me, I think, 24.4. And I'm going to use that to solve for the value of y. 24.4 subtracted off. I'm kind of too lazy to pull out a calculator here, so here's hoping. And that's going to be 3.6. Divide out the -3. And so I get y equals -1.2. All right, something important to kind of mention here, because this looks like I'm working with two Diophantine equations, and structurally they are, but Diophantine equations only really dealt with positive numbers. So here I'm getting negatives, and you say, well, I thought you couldn't get negatives, and I thought that they would all be whole numbers. Well, this is an extension of that standard form of a linear equation that allows for these sorts of things. You look at Diophantine as specific cases, like a subset of all of their types of linear equations. So I have an x value and I have a y value. All right, two linear equations, the way it boils down, possible solutions would be that they either intersect once, they never intersect, or they completely overlap. So I'd have one that overlays on top of the other. Let's see if I can get a change in color here. Doesn't look like it. Oh, hold on. We got something going on here. Got a pulse. All right. Kind of hard to tell. I tried to sort of distinguish them a little bit from one another. See if I could pull this out. You see we have the black and the red. They overlay, occupy the same position. All right. So this first instance would be exactly one solution. The second case would be no solutions. And the last case would be infinitely many solutions. All right. So that's what we're kind of looking at in terms of what our possible outcomes might be. In this case, we were able to obtain exactly one solution, which means that if I graph this line and I graph this line, they would cross each other at most once, or exactly once. All right. So my solution would be, we tend to write the x first because it's usually treated as an ordered pair, x comma y, 6.1, -1.2. All right. Now I stole their example, so let's see, without pulling out a calculator here. I think that's a different problem. Okay, so I stole their example, which ended up not having any solution. All right, well, I'm sorry, it has a solution. We just figured it out. It's just they didn't provide a solution in the text. But let me do a quick check. So I'll grab one of the two original functions. I'll take the second one this time. I don't have to put the 1 in front of the y, but I did it anyway. All right, so I'll replace the x with a 6.1 and the y with a -1.2. So that's going to give me a 12.2 minus a 1.2, which would be 11. So that checks out. And if you really want to be sure, take the other one and see if that plays out also. So 24.4 plus, that's going to be 3.6, which does equal 28. So that checks out also. All right. So that's the addition elimination method with a little bit of substitution mixed in. There's a lot going on there. This lesson talks about Cramer's rule, which I'll walk you through, but you can see there's a lot of this it's another case where there's just kind of a lot going on, right? So yeah, I'll take it. I'll use that example, the one that I just went over, because I think it's probably going to be the easiest to sort of play that out, right? So yeah, so let me just show you with this one, and then we can look at some of the other examples. I think that's probably the best way to handle it. Now, I am going to kind of caution you that this explanation does not really get into why Cramer's rule works. If I have a little bit of time, I mean, I'll make the time at some point. It's just a question of, like, in the next week or in the next month, to just kind of give a little primer or explanation on where this comes from. It involves, or at least the proof that I use or the demonstration that I use involves some other linear algebra techniques that I would want to go over just to kind of make it a little bit more of a robust explanation. But for now, I'm just going to walk you through the process. So what we do is we really strip away anything except for the coefficients, and we write it in the form of a matrix. All right, a matrix of values. And really, you just think of a matrix as a set of rows and columns that contain information, right? And the information that we're working with is numerical. So here, it's associated with just the coefficients, needs to be in the appropriate form. So it needs to be in that nice Diophantine form, which is something x, something y, then the constant, the one that doesn't have a variable. But I'm going to take those values, those coefficients and constants, and make kind of a little mini spreadsheet out of it. All right. So the way we handle this is that this is equation 1, equation 2, this is my x variable, my y variable, and this is my constant. All right. So we need 3 additional matrices that we're going to use as our way of carrying out Cramer's rule. All right. So the first one we're going to call D. D stands for determinant. That's going to involve just the x and y. All right. So a determinant, among other things, is really just the value we can think of as a good way of saying it, the value of a matrix. All right. So I'm looking for the determinant of these coefficients, and all we have to do to find that determinant is multiply down the diagonal, the main diagonal, which is upper left to lower right, and then lower left to upper right. All right, so 4 times 1, and then 2 times -3, and subtract the results. All right, so that's going to give me a 4 plus 6, which is 10. All right. Then the next thing we're going to do is we're going to find the determinant for, it's kind of weird without giving all the background stuff, but determinant in the x variable, which involves us replacing our x coefficients with the constant coefficients. So we'll do constant against y. So 28, 11, -3, 1. So same deal, down the main diagonal, which is upper left to lower right. So 28 times 1. And then lower left to upper right, 11 times -3. Then subtract the results, which is 28 plus 33, which is going to be equal to 61. then determinant in the y variable, which is going to be the x coefficients 4 and 2 against the constants 28 and 11, upper left to lower right, then lower left to upper right, multiplying, subtract the result, 44 minus, that's going to be 56, which is going to be negative 12. All right. Now the x solution, x is going to be equal to whatever you got for d sub x over d. The y solution is whatever you got for d sub y over d, which is going to be 61 over 10, negative 12 over 10, which is 6.1, and negative 1.2. All right. And that happens to be what we got earlier. And that is an application, or the application, of Cramer's rule. It doesn't really get into how or why Cramer's rule works, even in the slightest, but it is a correctly carried out process. And like I said, I'll try to make another video that kind of walks through a little bit more of the foundational stuff behind this, because this looks like hocus pocus at this point. Like, oh, this came out of nowhere. So yeah, I'd like to give a little bit more background on that. Some of it comes from the review of determinants, but even still, it doesn't really get at the hows and the whys. Really just the whys. And the solutions themselves, even though they follow the technique, they don't really get into, again, why things work the way they do. But at this point, you should be able to practice these concepts. Some of it involve writing the equation, the set of equations first, and then coming up with a solution. But they're all essentially based off the same concept. All right. So the requirement here is that you do it using Cramer's rule, but I would also encourage you to give it a shot using the additional elimination method. All right. So it's a valuable connection. So that's important stuff, especially moving forward. All right. So like I said, you're good now for 3.2.2.